So today I am presenting this paper which explores on how different bite sizes of diphosphine ligands results in tetrahedral distortions of square planar complexes and how diphosphine ligands with larger bites can stabilize nickel 1 and palladium 1 complexes. So we know nickel 2 and palladium 2 are D8 metal ions. So D8 complexes in square planar geometry are diamagnetic, while in tetrahedral geometry they are paramagnetic. So thus, in order to form square planar complexes, we need strong field ligands like the ones with phosphorus as the donor atom. Now the reason is phosphorus, because it has unoccupied d orbitals, they can act as pi acceptor ligands. Now in this experiment, they have synthesized nickel 2 and palladium 2 complexes of these two forms. Here, the two bidentate ligands are same, and here the two bidentate ligands are different. And they have been synthesized from this octahedral complex of nickel and appropriate ligands, and then they characterized it by 31p NMR. So the bidentate ligands that were used have different bite sizes as shown. So here there is just one carbon spacing. In 2, 3, and 4 there are 2 carbon spacing. In 5 there is 3 carbon, and in 6th one there is 4 carbon spacing. Now this is here we can discuss the electronic absorption spectra of the complexes. Here we can find the nickel 2 complexes exhibit a electronic absorption from 400 to 500 nanometer. This band is assigned to a transition from A1G to B1G orbital. So it is clear that especially when you consider this nitromethane, the one in nitromethane and dichloromethane solvents, as the bite size increases, the lambda max is also increasing. Well, in when done in acetonitrile solvents, it is found that there is some abnormality. This is because when the complexes contain this DPPM ligand, there is a tendency that acetonitrile can coordinate with this complexes, forming a pi coordinate complex. That is the reason behind this abnormality. Now, in this data, we will focus on the halfway potential of nickel 2 of the nickel 2 nickel 2 1 couple. So here again we can see that as the bite size increases, the halfway potential becomes more and more positive. So this is again a clear indication that as the bite size increases, the stability of nickel 1 complexes also increases. A similar trend is also seen in case of palladium complexes, where we can see in all these cases there is no palladium 1 complexes formed. They were directly forming palladium 0 complex. But it was only in the case where the ligand was DPPX, that is the one with the largest bite size in this experiment, only that could stabilize this palladium 1 complex. So here we have different bite sizes or the spacings between the two phosphorus donor atoms and the bite angles that are formed. So we can see again as the spacings or the bite size increases, the bite angle is also increasing. So to understand how chelate ring size affects the structure of complexes, X-ray diffraction studies of the nickel DPPM twice 2 plus and nickel DPPB twice 2 plus ions were carried out. So in this compound, that means where the ligand has only one carbon as the spacing between the two phosphorus donor atoms, it was found that the bite angle was small, that is 73.2 degree, and this molecule was strictly planar. There was no tetrahedral distortion and the dihedral angle was 0. But the case is different when the bite size increases and becomes this compound. And here it was found that the bite angle was 85.2 degrees, and there was a significant tetrahedral distortion with a dihedral angle between the two planes given here, between the defined by the two phosphorus atoms of each ligand to be 24.1 degrees. So, well, we can say that this can be because of the steric interactions, and to reduce the steric repulsion between the alkyl groups, they actually resort to these tetrahedral distortions. But there is an electronic picture to it as well. So, to understand this relationship between chelate angle and the dihedral angle, extended Huckel molecular orbital calculations have been carried out for this model compound nickel pH342+. So here, this particular picture actually shows the behavior of frontier molecular orbitals of nickel of this compound, this model compound, as a function of beta, which is in the x-axis, and the alpha is fixed at 85 degrees. So on this side, we have here the beta is 0, so it's strictly planar, and here the beta is 90 degrees. So, and we can find that these orbitals truly represent the orbitals of square planar complex. So we can see as beta increases, one thing we have to note is that the antibonding interactions between the ligand orbitals and the metal orbitals on the xy plane decreases, while the interactions with the orbitals in the xz and yz orbitals will increase. Because of this dihedral twist, they are no longer in the plane. So because of this reason, dxy orbital goes down, and note that instead of dx square y square we have used dxy. This is we have chosen such a coordinate system to show tetrahedral distortion more easily. So this is the dx square y square, and this is the dxy. Here we have just shown it in this way. So the dxy goes down. Dx square, earlier it was also a non-bonding, and now also it's non-bonding. While the dz square also gets lowered in its energy, because earlier it was slightly anti-bonding, but now again it decreases, but again only gradually. While the dxz and dyz increases in its energy. So the two main things that is happening is stabilization of dz square and destabilization of dxz and dyz. So at an optimum beta angle, the energy would be minimum, where there is a balance between these stabilization and destabilization of all. So from these calculations, it has been found that for this alpha equal to 85 degree, the beta was 25 degrees, which is very much close to what we have seen in this case. Here it is 24 degree for 85.2. Now to explain the trend in the absorption spectra, it's very clear that dz square decreases in its energy slowly than compared to this decrease in the dxy energy, orbital energy. So altogether, we can say as beta increases, the energy gap between this dz square and dxy decreases with increase in bite size. So that is the reason why lambda increases as the bite size increases. Now to explain the half-wave potential again. So for reduction, the one extra electron has to come to this LUMO, which is the dxy orbital. And to stabilize this incoming electron, the dxy has to drop in energy. So again, same reason, as bite size increases, the tetrahedral distortion would be more. So beta would also, the optimum beta where the energy minimum would be there, that will also be greater, and hence dxy would be dropped more, will drop in energy more, and hence the nickel 1 or palladium 1 complex would be stabilized much more. Now this theory has also been verified with an with the experimental value where the LUMO energy at the optimum beta value were calculated and given and normalized, and which has been put under E half calculated, and it is very clear that these values are very much close to the observed experimental half wave potentials. So thus we can say that increasing the bite size can cause tetrahedral distortion, and this is because not just because of steric interactions, but it can also cause a stabilization considering the electronic factors. Thank you.